In this video, we're going to look at two factors that influence the effectiveness of buffers and two related concepts of buffer capacity and buffer range. So as we know, a buffer is composed of a weak acid and its conjugate base, or a weak base and its conjugate acid. And buffers work best when the concentrations of the weak acid and its conjugate base are as high as possible. So the higher the concentrations of the buffer components, the more effective the buffer is going to be at resisting changes to pH. It also turns out that the buffers work best when the concentrations of the buffer component, so that is the weak acid and its conjugate base, or the weak base and its conjugate acid, are similar to one another. And in order to be most effective, we want them to be within one order of magnitude of each other. So we want the concentrations to be within a factor of 10 of one another. So first, a simple example to see how the concentration influences how effective a buffer can be at resisting changes to pH. So in this example, I've got 1 liter of 2 buffer solutions, and each one is composed of acetic acid and acetate ions. And I'm going to add 0.01 moles of hydrochloric acid, a strong acid, to each one of these buffer solutions. The difference is solution A is more concentrated. I have 5 molar acetic acid and sodium acetate ions. And in solution B, I have 0.05 molar acetic acid and acetate ions. And so we can see, right, both solutions resulted in minimal changes to pH, so they both effectively acted as buffers, but the change in pH of the more concentrated solution was even significantly less than the change in concentration of the more dilute solution. So the more concentrated the buffers, the better the buffer is at resisting changes in pH. So a related concept is that of buffer capacity. So we know that buffers work by having both a weak acid and its conjugate base present. And so the addition of any strong acid or strong base is going to react with the buffer component. So if I had strong acid, it's going to react with the weak base component of the buffer. If I had strong base, it's going to react with the weak acid component of the buffer. And so these buffer components react with the acid or base that we're adding. But we only have a finite amount of them. So if I add more strong acid or strong base than I have of the required buffer component, we're going to exceed the buffer capacity. So the buffer capacity is how much we can add without destroying a buffer's effectiveness. And just a quick example. So if I took the same solution B from last time, but instead of adding 0.01 moles of a strong acid or strong base, now I'm going to add 0.06 moles of sodium hydroxide. And so now I've added more moles of sodium hydroxide than I have moles of the weak acid. And so when I make my BCA table, it's the acetic acid that's the limiting reagent, right? It actually runs out. There's leftover strong base that it wasn't able to react, and now I have a huge change in my pH because I've added so much strong base that I've exceeded the capacity of the buffer. So the second idea is that we want our buffers to be the best. We want to have similar concentrations of the weak acid and its conjugate base. And ideally, the concentrations would be the same. And so if I have just a hypothetical buffer and I make the concentration of the conjugate base and the conjugate acid the same, then inside the log here, this fraction is going to be 1. Right? And the log of 1 is going to be 0. So when the concentration of the weak acid and the conjugate base are the same, the pH is equal to the pKa of the acid that makes up the buffer. And so what this tells us is that buffers work best at maintaining pHs that are close to the pKa of the acid. So on the previous slide, we saw that buffers work best when the pH we're trying to maintain is close to the pKa of the acid. But how far away from the pKa of the acid can we get and still have an effective buffer? Well, if we come back to an idea from the first slide, right, we want the concentrations of base and acid to be within a factor of 10 of one another. And so we're going to use this to calculate the range of pH values in which a particular buffer would be effective. And so we know that we want to be close to the pKa. And so if I look at sort of the upper limit, And I'm going to have a solution where the concentration of the base of the buffer is 10 times the concentration of the acid. So that's going to be 10 over 1. And the log of 10 over 1 is going to be 1. So the upper range of a buffer is going to be 1 over the value of the pKa. In the lower range, let's say the acid was 10 times more concentrated than the base. So now I'm going to have the log of 1 over 10. The log of 1 over 10 is minus 1. So the range of pH values that a particular buffer system is going to be effective is going to be the pKa plus or minus 1. So that's how we know what pHs a particular buffer system will be good for. All right, and I have a follow-up video doing some calculations involving buffer ranges.